Okay, so this recorded lecture corresponds to topic 8, corresponding to chapter 6 in my current textbook, using probability to make decisions about data, just kind of an introduction to probability. All right, so let's start with a review. We've already talked about the total area under the standard normal curve. It adds up to 1, okay? It's just the frequency of all the scores, right, underneath the curve. So we know that 68.26% of all scores in the normal curve are going to lie within one standard deviation of a mean. So a z of +1, a z of -1. If we add those up, we get the proportion of scores that are within one standard deviation of the mean, which is 0.6826, or the percent, which is 68.26. Okay, so a quick review. A z-score is a deviation divided by a standard deviation, and we can use that to standardize any score. We can also use a z-score to find the probability of a given outcome. Probability just refers to the likelihood of an event occurring expressed as a proportion. So a proportion of the area under the curve where that event is occurring, right? So a probability of 0.50, for example. 1 in 3 odds is not a probability, not really odds. 21% chance of winning isn't a probability either, but it's pretty darn close. We just need to move that decimal over to make it into a probability, and we would say P equals 0.21. Something that can never occur has a probability of 0. Something that will occur has a probability of 1. So as far as statistics goes, there is no such thing as P equals 0 or P equal 1. All right. If you feel tempted to write P equals 0, you should be writing P less than 0.001. Probability is about the future or about hypothetical distributions about what would be, right? So it's about predicting what can occur under given circumstances. Things that have already happened in the past, they either happened or not, right? There's no probability to that. So why do we even care? Probabilities are the foundation of inferential statistics. We want to make inferences about the population based on our data. So we have to figure out how likely it is that we would obtain that data, the probability of obtaining that data given a certain population probability distribution. We're doing this because we're using null hypothesis significance testing, okay? We could be doing, so probability is also the basis of Bayesian statistics. In this class, we're going to be null hypothesis significance testing, and this is basically finding the probability of obtaining sample data given a theoretical distribution, which is the null hypothesis. Okay, and we'll get back to that in a minute. We're going to use probability to ask questions like, if the mean for the population is X, how likely is it to get a sample mean of Y? Okay, so for example, if mean statistics scores for all students in the United States, taking first-year statistics, is 75, maybe I want to know if my students are better and worse. I'm a new teacher at this institution, right? So I might be better, I might be a better teacher, or I might be worse. So I'm going to test my teaching against the national average. So maybe I have all of you guys, all my students, take a test and you get a mean of 70, and the national average is 75. And we can say, do you guys belong to the same population of statistical knowledge as the national average, right? So I have you guys, how likely is it? And I'm going to explain how to do that later. We also might ask questions like, if our sample mean is Y, what can we expect the population mean to look like? And we'll build confidence intervals, which is a range of values that we can expect the population mean to look like based on our sample. Okay, so more terminology. An event just refers to the outcome of a trial. For example, if we flip a dice, we can get heads or tails, right? If with that flipping the coin, not flipping a dice, flip a coin, that is one trial. The outcome is either heads or tails would be the event, right? If I roll a die, right? If I roll a die, there are 6 possible outcomes, 1, 2, 3, 4, 5, 6. If I get a 6, that is an outcome, an event, right? If something is exhaustive, it's a set of events that represents all possible outcomes. So in my example of rolling a die, there are 6 possible events. That's exhaustive. If I flip a coin once, all possible outcomes are heads or tails. That's exhaustive, right? Mutually exclusive just means that if one event happens, the other one cannot happen. So the occurrence of one event precludes the occurrence of another. For example, if you flip a coin and you get heads, you cannot possibly get tails, right? The events are mutually exclusive. If I roll a die and get 6, I cannot get 1, 2, 3, 4, 5 because they are mutually exclusive, right? One side comes up. What about a 2 of hearts? 2 in hearts. If you draw a card out of a 52 card deck, you can get both a 2 and a heart. Okay, they are not mutually exclusive. More terminology. Independent. Events are independent when the occurrence of one has no impact on the probability of another. Now we're going to kind of get back to this and when we get to chi-square, right? But for example, if you flip a coin once and you get heads, that has no impact on the likelihood of getting heads on the next flip of the coin. If you flip a coin 20 times and get heads every single time, the likelihood of getting heads on the next flip is still 0.5. Okay, it doesn't mean you're going to be more likely to get tails just because you've gotten heads 10, 20, 50 times, right? The next flip is totally independent. What about if you draw a card from a deck of cards and you get a 2 of hearts, like we talked before? Does this impact your chances of drawing a 3 of hearts in the next draw? It depends on whether we replace the card or not. When we drew that first 2 of hearts, we had a 1 in 52 chance of getting a 2 of hearts. If we put the heart back in, our chances of getting a 3 of hearts is 1 in 52. But if we don't put the 2 of hearts back in, our chances is 1 in 51. These events are not independent. They are dependent, right? If it's replaced, the events are independent. If the 2 of hearts is not replaced, it's dependent or not independent, right? So dependent just means the probability of one event occurring is influenced by the occurrence of the other. So when we replace that card, it's called sampling with replacement. Okay, this is when we put the card back in. In your fancy textbook terminology, previously selected individuals or events are replaced back into the population before drawing an additional one. This means it results in independent events, right? If sampling without replacement is when you don't put the card back. Previously selected individuals or events are not replaced into the population before selecting again. This results in a dependent event. The second one's dependent. Okay, more terminology. Odds, you don't talk about 1 in 3 or 1 in 66. You express them as fractions or ratios. 1/66, or you could also write, theoretically, if I get a pen, I get it. You could also write 1:66. All right. We can also express odds like that. All right. Probability is expressed as a decimal. We've already talked about that. P equals 0.015. Chance is expressed as a percentage, like 1.5 or a 20% chance of rain, or it actually sprinkled today, but maybe a 0.002% chance of rain and a 20% chance of wildfires in California, right? Probably 50%. Okay, moving on. So let's walk you through an example that I got from an older professor that I really like. Okay, say I bought a scratch-off lottery ticket. How likely is it that I win? Okay, the California Lottery website lists the odds. You can also, in many tickets, just flip them over and it'll have the odds, okay? What are these odds? A way to express how likely it is to win a ticket. Now, most of us don't fully understand that, so for your benefit and to demonstrate the principles, we are going to walk through it. Okay, so this would be on the website or on the back of the ticket, right? And you can see that on the left-hand column, you have game prizes, and on the right-hand column, you have the odds, 1 in whatever. And total winners is how many tickets there are that actually have it. So here we see game prize ticket. You have 1 in 12 odds, right? 1 to 12. And there are 1,330,560 tickets that the prize is another ticket. All right. The overall odds of winning some sort of prize is 1 in 4.78. What does that mean? So let's think about it. That means 1, remember, odds should be expressed as a fraction. You can divide 1 by 4.98. You equal the probability, which is 0.209. This means that about 1 in 5 tickets are winners, 21.9, right? You have a 20.9 chance of winning. If you buy 5, you're likely to have one, right? If you do win, which is the most likely prize? A ticket, right? So how likely is it that any ticket you buy is actually going to be a free ticket winner? 1 in 12, 1 divided by 12 equals 0.083, which is an 8.3 chance of just getting a ticket, which isn't very exciting, right? What about winning that $500, which in this ticket case is the most you can win, right? 1 in 480,000. You just have to divide that to get 0.0000208. So you have a 0.00208 chance of winning $500. Not really worth it, is it? Right? You might as well, for those kind of odds, you might as well just go get, a mega millions or something like that. Mega millions, you're much less likely to win, but the difference is infinitesimal. Really, you're still not likely to win. And, don't get 5 different combinations for mega millions, because the increased probability for winning between getting 5 versus 1 or even 50 versus 1 is so small as to not be meaningful. There are 3,300,000, okay, over 3 million winners out of how many altogether? Okay, if 20.9% of tickets are winners, then we have to divide to find that there are approximately 16 million tickets printed. Well, that's a lot of money, right? Not a lot of winners. Okay, ways to express probability. Probabilities are expressed in proportions, right? P equals 0.18. But you can also talk about percentages, 18% of the time, 18 out of 100. You're going to turn it into odds. So 0.18 is just 1 over 5.55, right? So these are just a little review. Now, why does all this matter? This matters because we are going to be talking about probability distributions, and we need to distinguish a couple things. First, a probability distribution is just the probability of all events in a population. We saw the standard normal curve and its probability distribution, right? There's 2 main types. There's the empirical probability distribution, and this is created with data, okay, by estimating the relative frequency of every event in the population, or based on observation of samples from that population. This is collect real data and then base our estimates of the population on the samples, right? A theoretical probability distribution is just a theoretical model, okay? Like that standard normal curve, that's a model. When we actually used data and we added that normal curve to our histograms, we saw that most data does not exactly follow perfectly on the theoretical normal distribution. They approximate it, right? Theoretical probability distributions are our hypotheses, reflect our hypotheses about what nature looks like, what the construct we're interested really is in nature, right? So we're going to get to that, but a theoretical probability distribution is, for example, how we expect events to be versus how we expect them not to be. So the researcher's experimental hypothesis versus the null hypothesis, and we're going to get there in a minute. So we saw normal distributions, right? Areas under the normal curve can be thought of as probabilities, and we're going to use this to test hypotheses, okay? The proportion of the total area under the normal curve for scores in any part of the distribution equals the probability, right? Think about relative frequency. If the proportion of scores at Z greater or equal than 1.5 is 0.0668, we can say the probability of the score being 1.5 standard deviations or greater is 0.0668. So let's have a look at that. For example, right here, we can see, as we've talked about many times, that the proportion of scores that are going to be greater than 3 standard deviations from the mean is very, very small, 0.0013. Okay, that's the proportion. So the probability of any score being greater than 3 standard deviations from the mean is 0.0013. All right, and you could just, any amount of things in any distribution, an empirical distribution, you would divide, right, the frequency. You just divide the frequency of these, for example, within 1 standard deviation of means, all these scores by the total, and we're going to get that proportion, relative frequency. My voice is going. Okay. So more terminology. We saw this a couple weeks ago. Greater than or equal to, scores that are higher than a certain value, less than or equal to, less than, and importantly, more extreme than. This just means the scores are more extreme in either direction. So let's walk through that a little bit. So here we see the probability of Z being within 1 standard deviation of the mean, right? You see right here. We just have to add up 0.3413 and we get 0.6826, which I've been repeating this whole time. 68.26 of scores in a normal distribution are going to be within 1 standard deviation of the mean. Okay, so what about the probability of Z being greater than 2? Right? We know that's not too big, right? But we can see the proportion of the scores in a normal curve, right, of being between 2 and 3 is 0.0215 and greater than 3, as we already saw, 0.0013. We can add them up. We get 0.0228. For the other tail, the probability of Z being less than -2, it's the same proportion as before. So the probability again is 0.0028. Okay, what about more extreme than, right? It's just both ways. More extreme than 3, it's greater than +3 and less than -3, right? Okay. So I think I'm going to pause here and then we'll do the second part to separate the video.